Hello, calculus scholars. Um, Today we're going to be happy snow day. We're going to be opening up the optimization week when we get back next week. And what I thought we would do today is go in depth into what optimization is and give you a set of notes coming into optimization week so you have a good understanding of what optimization is. So just a reminder of what you should be doing today or this weekend and into Monday when I see you next time is to one, make sure your scale 32 particle motion IP is done. Watch this video and take notes on this video to learn what optimization is. And then be sure that you are showing me the 32A notes and the notes for this video when I see you on Monday. So what optimization week is going to look like when we get back is we're going to really be zeroing in on a box problem on the first class next week. So we'll kind of build off of this video and you'll actually get to interact with a physical example of the box problem. And you'll kind of get to learn how to model and learn about the concept of maximization. And then there'll be group work on specific types of optimization problems that you and your group get to choose. And there's about 4 types of problems that I have that range from like geometric in nature to maybe more of like a physics type of example to economics. And you get to come up with a tangible solution and present it to the class. So today, please have your notebook out as we develop the concepts and theories of optimization. So optimization is in a lot of different fields that use calculus. So the economist might use calculus and maximize profits and revenues and the decision-making of an individual firm or business. A physicist might use calculus to find the maximum height of something, or the engineer might try to optimize or maximize the space design when dealt with scarce materials. So next week, we're going to kind of go through this strategy of being able to solve optimization problems. So the first thing we're going to do is kind of take apart the problem and understand it, then develop a mathematical equation of the problem. And then 3 through 5 is just using our knowledge of calculus to solve it. So if you know how to take a derivative and you know how to find a critical point, you'll be able to solve the optimization problems really well. And then lastly, interpreting solutions. So I'm going to start with a very basic number sense type of problem. And this is going to help introduce the concept of optimization. And I'm going to show you the before calculus way and the calculus way. So in the BC way, before calculus, and find 2 numbers whose sum is 20, whose product is as large as possible. You choose numbers that add to 20 and you look at the product. This means multiply. So maybe I do 1 and 19. I'm going to try that and I'm going to get 19. Then maybe I know that 2 and 18 add to 20. So I'm going to get 36. 3 and 17. And this is going to get very long-winded, but eventually you'll get down to 10 times 10 and you could kind of compare that to 11 times 9 or like 9 times 11, and you'll see that 10 times 10, kind of wins out. Now, another way that you could do this is you could say, let's suppose A plus B equals 20. And we can also say here that B is equal to 20 minus A. With this equation. And you're going to see why I'm going to do this here in a minute. We want to maximize A times B. Now, the problem is that my equation here is in two variables, but I got 20 minus A equals B. So I'm going to rewrite this problem as maximize A times, and we get a different color of annotation here, 20 minus A so effectively, we want to maximize 20A minus A squared. So to do this, the simple idea is to take the derivative and set it equal to 0. So if we do that, we're going to say that 2 minus 2A hold on, this is 20A. So we have 20 minus 2A equals to 0. And I'm just going to add 2A to both sides and solve for A. And divide by 2. So we get that A equals 10. And then if A plus B equals 20, I'm going to plug in my 10. And I can see that B is also equal to 10. Now, for this particular problem, I do think kind of doing it the numerical before calculus way is kind of illustrative to see the concept of optimization, and that the calculus way might be a little overkill. But for a lot of the real world problems that we're going to see, the calculus way is going to make things a lot easier. Let's look at a geometry problem. It says that an open top box is made to be from a 20 to 25 sheet. Based off of a given image, how large should the corner squares be made to maximize the volume? So the volume of a box is length times width times height. So I like to always just start with the geometry formula. So when we cut the box, 25 is what we start with, but when we cut things out, we're cutting 2x. So we could say that width is equal to 25 minus 2x. Our length, we're also cutting, 2 corners out. And then this x piece, when you fold the box, it actually becomes the height of your box. So we're actually going to plug these into the formula. So you're going to have 20 minus 2x times 25 minus 2x times x. And we do have, some multiplication, to kind of be working on. So we'll take care of that. So 20 times 25. It's going to be 500. Just multiply, 2 things at a time. Minus 40x. Minus 50x. Plus 4x squared. All multiplied by x. So our goal is to maximize. We got this all in one variable. Our goal is to maximize 500x minus 90x squared. Plus 4x cubed. That's our goal. So to do this, we're going to take our derivative and set it equal to 0. So when we do that, I'm going to get 500 minus 180 x plus 12 x squared. And the question is this going to be factorable, or do I want to maybe be thinking about like the quadratic formula? One thing that can kind of help me here is just kind of pulling out that GCF. So obviously, 12 doesn't go into 500. But 4 goes into 500. So I could just pull out 4s. So I have 4 times 125. And 180 divided by 4, it's going to be 45 x. plus 3x squared. And then we want to use factoring or quadratic formula to solve this. And just to save us a little time here, I'm not going to get into the uglies, but this is the equation. We're basically maximizing the volume. And we use the quadratic formula. That's like, opposite b plus or minus the square root of b squared minus 4ac. Over 2a. So effectively, we kind of did write this a little bit in reverse order, but the a is equal to 12. The b is equal to negative 180. And then the c is equal to 500. And you're going to effectively go to your calculator, or there's also quadratic formula calculators online. And you're going to be able to see how we got to that 3.681. Let me just kind of demonstrate how we could use this quadratic formula calculator. So my suggestion for the sake of efficiency would be to go to a quadratic formula calculator and just enter in the numbers. So A was 12, B was negative 180, and C was 500. And they give you two solutions. So note that the 11 solution is not practical because, if we cut off 11 feet from both sides, that's more than 20 feet and we're not going to have a width. But it is practical, however, to have that 3.689. We're going back to that problem. All right, so the last type of problem is what I call the profit maximization problem. So profit effectively is revenue minus cost. So if you're going to the farmer's market or something like that, and you're running a business, revenue is the amount of money that you take in. And then cost is going to be, things like what would it cost to produce something? And you have to take that away, from the money that comes in. So if I'm selling like ground beef at the farmer's market, for instance, sure, I may be, selling ground beef for $10 a pack and earning that, but then I also have to subtract the cost that it took for me to produce that, like let's say put it into package or operate my farm. And then marginal, when you see this term, marginal effectively means change in. So it's basically the economist way of telling you to take the derivative. And you may want to write these down here just to kind of give you some bridge between calculus speak and some of the common economic vocabulary. All right, so let's take a look at an example here. So it says, suppose that the revenue is given by 9x and the cost is given by x cubed minus 6x squared plus 15x. Find the value of x for where the profit is maximized. So our goal is to maximize profit. And this can be better said as our desire to maximize revenue minus cost. So to carry this out, our revenue, which is 9x, and then our cost is minus x cubed minus 6x squared plus 15x. And we want to maximize that. And I like to stop writing maximize when I take the derivative. One thing that I can do is just rewrite this before I take the derivative so that my like terms are combined. That's negative x cubed plus 6x squared. And then I have a 9x minus a 15x. That's going to effectively get me to negative 6x. So now I'm going to take the derivative and set it equal to 0. And I'm going to do, when I do that, I'm going to say that I have negative 3x squared plus 12x minus 6 equals to 0. I'm going to pull out a negative 3. So I have x squared minus 4x plus 2. And I'm just going to set that equal to 0. And then I want to, use factoring or, some type of quadratic formula. So actually, I'm just going to kind of do quadratic formula here. So I'm going to let a equal 1, b equal to negative 4, and c equal to 2. And if I were to actually outright compute this by hand, my opposite of b is just 4 plus or minus the square root of 4 squared, which is 16, negative 4 squared, which is 16, minus 4 times 1 times 2 over 2a. That's just 2 times 1. This is equal to 4 plus or minus the square root of 8 over 2. So we could say that this is either going to be 4 plus square root of 8. And when we say square root of 8, we can just kind of convert this into decimal form, make it kind of more like real life. That's about 2.82. So we could have 4 plus 2.82 over 2, or 4 minus 2.82 over 2. And when we do that, we have 5.82 over 2, or 6.82 over 2, I should say. Or 1.18 over 2. And we're going to get some decimal numbers. So we have like a 3.41. And then we have like a 0.5 as well, or maybe a little bit more than that. 1.18 divided by 2, 0.59. And we may want to even like, look at a sign chart. Like 0.59 and 3.41. And I want to make sure that my critical points are critical points, and I could test out what my maximum and minimum are going to be. So I want to plug it into the derivative that I found. So I'm just writing the derivative off to the side. So if I plugged in like 0, I would have a negative number. If I plugged in 1, so like if I did -3 times 1 plus 12 times 1 minus 6, I'd be at a positive. And then if I did a number that was bigger, like let's say, -3 times 4 squared, that's like a -48. This is going to actually go back to a negative number. So I can kind of see here that the graph is probably going like that. So the 3.41 is the maximum. You could go to Desmos.com and graph as well and see what the relationship is looking like too. But this is a good functional analysis type of way of solving a maximization problem. So you'll get your hands dirty next week with a lot of these type of problems, but I wanted you to get exposed to these today and over a weekend, so that we can really start diving into these type of problems. Pretty exciting problems next week.